Problem 1.17 gives us an unstable particle that spontaneously disintegrates with a lifetime of tau. So, in this case, the total probability of finding the particle is not constant, but rather decreases over time. And what we say for that is that p of t at any t is roughly proportional to some function of the form of an inverse exponential with the power of negative t over tau, where tau is our lifetime. So, one way that Griffiths suggests for achieving this result is that we no longer assume that the potential v is real. So, sort of in 1.24, which is where we sort of started deriving the preservation of normality, one of the things we assumed was that v, which is the potential energy, is real. And as we will see, as we sort of delve deeper into quantum mechanics, this isn't necessarily required. Having a real potential leads to conservation of probability, which is sort of enshrined in equation 1.27, which is this conservation of normality thing, where we say that the probability at any point in time does not change with respect to time. This is only true if we sort of assume that our potential is real. However, if we assume that our potential has imaginary components, such as, for example, instead of saying v just equals v naught, we can say v equals v naught minus I tau, where tau is some constant. And by sort of assigning this imaginary value to v, what we will find is that probability conservation actually is no longer maintained. Now, the actual physical significance of why we would do something like this is a little bit too esoteric for us to discuss this early on. But in general, in quantum mechanics later on, we will tend to see that imaginary numbers come to play a larger and larger role. And over time, hopefully, you will sort of get sort of a intuition on why we add imaginaries. But for now, unfortunately, at this point in time, we are just going to sort of blindly follow Griffiths' instructions and basically say, okay, Griffiths tells us to exchange our real potential v with an imaginary one, v naught minus I tau. And so that's exactly what we're going to do. And apparently, this is somehow supposed to prove to us that if we did this, we're going to get a probability that does, in fact, vary as an exponential decay. So let's start right away. Show that in place of equation 1.27, we now get dp over dt equals negative 2 tau over h bar times big P. So 1.27 basically says this in blue here, that basically the rate at which the probability changes with respect to time is equal to 0, and this was something that we required in order to preserve normality. Any sort of wave function that is already normalized must stay normalized with respect to time. So as a result, the change in probability over time must therefore equal 0. Now, this is apparently no longer true for a probability that does change with respect to time, one that exponentially decays. So this is sort of the first thing that we want to prove, is that dp over dt becomes sort of this expression. So let's just start this right away. So the goal here is to take a time derivative with respect to probability. So let's do that right away. So dp over dt is going to be equal to the integral from negative infinity to infinity. And remember, p is equal to the integral of negative infinity to infinity of psi star times psi. So we're just going to do chain rule here. So this is going to become partial psi star with respect to time multiplied by psi plus psi star with respect times partial of psi with respect to time dx. And if you're not sure how I got up to this point, what I did here was I recognized that p is equal to the integral from negative infinity to positive infinity of psi star multiplied by psi dx. So what I did was I took the derivative of p with respect to time, which becomes a partial of t with respect to this entire psi star times psi function here, and because of that, I then use product rule and sort of multiply everything out to get this expression in black up here. So, sort of the quintessential proof that we've been doing all this time in regards to preservation of normality is that we would replace these partials of psi with respect to times with partials of psi with respect to x's of second order by using the Schrodinger equation. So, we can do that once again here with the added sort of extra input, sort of the extra knowledge that v is no longer just a constant, it now has an imaginary component. So if we do that, what we're going to get is we're going to get expressions as follows. The partial of psi with respect to time is going to be equal to I h bar over 2m times the second partial of psi with respect to x squared. And once again, we're getting this by just plugging it into the Schrodinger equation and sort of isolating partial psi with respect to time. So minus I times v naught, which is our original potential that was real, over h bar times psi. And what we're going to get on once we sort of isolate everything is we're going to get this extra term minus big tau divided by h bar times psi. And what we've done here is we've taken the Schrodinger equation that we've used so many times before, and we've replaced v with v naught, with v naught minus I tau. So because of that, we get this extra sort of constant term here. And if we do the same thing with the complex conjugate, then we get partial of psi star with respect to time, and we're just going to change all the signs. So this is going to become negative I h bar over 2m times the second partial of psi with respect to x squared added with I times v naught over h bar times psi subtracted by a big tau over h bar psi, where all we've done here is we've changed the signs in front of all of the imaginary terms because this is a complex conjugate. Now we just sort of plug everything back into our original equation to get a new expression. So what we're going to get is, let's write that in dark blue. So dp over dt is going to be equal to and if we sort of write this all out, then partial psi star with respect to time times psi is going to be this bottom term. So let's actually label these, color code these to make this a little bit easier on ourselves. This is going to be equation 1, and then this in purple is going to be equation 2. So we're going to start with 2. So blue is going to be equal to the integral from negative infinity to positive infinity as before. And here, first is going to be our partial of psi star with respect to time. So we're going to do negative I h bar over 2m times the second partial of psi with respect to x squared plus I times v naught over h bar psi subtracted by big tau h bar times psi, and this whole thing is going to be multiplied by psi right here. So this whole thing is going to be multiplied by psi, and then we're going to add psi star, and then in green here, sort of the partial of psi with respect to time, which we already have in green, thankfully, so I don't have to rewrite it again. And then let's just add our brackets to this whole thing. And then finally, close off our integral with a dx. So, let's see. First off, obviously, as we've always done, every time we've done this proof, which is multiple times on various problems so far, there's always the cancellation of the potential term. So we have I v naught over h bar psi. Whoops, I just realized I did not include the conjugation terms, the star terms on all of these expressions. And they are supposed to be starred. My apologies. Let me just fix this really quickly. Right. So, one of the first things that we always do when we do this kind of proof that involves sort of dealing with the preservation of normality statement that we did earlier on in the textbook, one of the first things we can always do is we can cancel the potential. So if we look here, the same thing sort of applies. So we have I h bar, I v naught over h bar times psi star times psi here, which is like this term combined with this term. And then in the second sum, we have same thing, I v naught h bar, v naught over h bar times psi star, but this time with a negative in front. So instantly, these two terms sort of cancel out. So, and then after that, we also have sort of the same I h bar over 2m expression for the first two in these terms. So we can also sort of distribute that out. So let's write this in a bit of a neater way. dp over dt is going to equal the integral from negative infinity to positive infinity of, and we're going to start right away with I h bar over 2m times second partial psi star. Well, actually, let's change the order to make this a little bit neater. So this is going to be psi star times second partial of psi with respect to x squared, which is this bottom term right here. And I apologize, I forgot to add the conjugate psi star. There we go. And then we're going to subtract it by this top term, which is this combined with this. So this is going to be subtracted by the second partial of psi star with respect to x squared multiplied by just psi. And then finally, we have minus big tau over h bar psi star psi, and at the bottom we also have minus big tau over h bar psi starred. So these are sort of the exact same terms. So we're going to do minus 2 tau over h bar psi dx. So, well, actually, whoops, that's my mistake right there. I forgot to add the second psi. So this is minus 2 tau h bar psi star psi dx, because there's a psi and then a psi star and then a psi star and a psi. So hopefully we've sort of hopefully you remember if you've watched all the other videos, we've sort of gone over this expression, you know, tens of times now, at least. And this cancels out to 0 because we can sort of force these two expressions to equal each other by using integration by parts in one way on this term and in the other way on this term. So because of that, this entire expression just cancels out to 0 automatically. If you don't know how this is, I encourage you to look at some of the earlier problems. A lot of them have a proof that involves working with like taking a time derivative of probability, and in all of those we have sort of shown explicitly that this sort of just goes to 0. So dp over dt is going to be equal to simply the integral from negative infinity to positive infinity of negative 2 big tau over h bar times mag psi squared, which is just another way of writing psi star psi dx. And since the integral from negative infinity to infinity of mag psi squared is just probability, this is equal to negative 2 tau times h bar times probability. And what do you know? This is exactly what we were supposed to get for part A. So now that we have sort of the relationship that we wanted from part A, we want to go through with part B, which is a relatively trivial mathematical exercise, which is just to actually solve for P of t. So if we look at this, obviously we can sort of solve this by taking advantage of natural logs. We can just do dp over dt, and then if we divide both sides by p, this is going to be equal to negative 2 times big tau over h bar. From here, if we sort of take advantage of the fact that this is the derivative of a natural log function, we can say that d over dt of the natural log of p is going to be equal to negative 2 times big tau over h bar. And then from here, we integrate both sides with respect to time. So this gives us natural log of p is going to be equal to negative 2 tau h bar times time, and then we're going to add some average constant to it. And then from here, exponentiate both sides, and we get p equals some constant times e to the negative 2 times tau over h bar multiplied by time. And from here, this is sort of the same form as what we wanted before, e to the negative t over tau. So this is proportional to e to the negative t over tau. And part B wants us to find the lifetime tau. So tau, evidently, so negative 2 big tau over, whoops, that is a very horrible one. Big tau over h bar is evidently going to be equal to negative 1 over tau. So therefore tau is equal to h bar over 2 times big tau. And this is the half-life of our particle. Or not half-life, but lifetime of our particle that was given to us originally when we did e to the negative t over small tau. So it's our lifetime.